Hey everyone, and welcome to This Explainer. I am absolutely thrilled you're tuning in today because we're going to demystify something literally foundational to the digital world we all live in. We're looking at the invisible mechanics of the internet. Specifically, we're breaking down two concepts that are just constantly working behind the scenes to make our connected lives possible: packet switching and routing.
So how does data actually travel from point A to point B? It seems like a simple question, right? Now, if you've ever looked into networking, you've probably heard terms like switching and routing. And, if you're relatively new to this, it's incredibly easy to use them interchangeably. I mean, they both sound like they do the exact same thing, moving stuff around. But honestly, they are entirely different beasts. They're these distinct, highly specialized mechanisms designed to solve a huge problem, sending massive files, like your 4K streaming video, or a huge software update, across incredibly crowded networks without the whole thing just crashing to a halt.
Okay, let's dive into this. Here's our roadmap for today. First up, we're unpacking packet switching. Second, we'll get into the mechanics of routing. And third, we'll look at the modern network synergy.
Part 1. Unpacking packet switching. Okay, so when you send a file, it doesn't just travel as one giant continuous chunk. Instead, it's intentionally sliced up into these small, standardized units called packets. Each packet carries a tiny piece of the original data. But crucially, it's packed with control information, like a source and a destination address. And here is the wild part. The network treats every single packet like an independent rogue agent. They can take completely different paths to get to the same place, and they might even arrive totally out of order.
And this brilliantly illustrates how the network handles the chaos. It uses a highly mechanical journey called the store and forward mechanism. See, when a router encounters a packet, it doesn't just blindly pass it along. No, it follows a strict sequence. First, it receives and temporarily stores the entire packet. Then, it checks for any data-corrupting errors. Third, it calculates the optimal output port for that specific moment in time. And finally, boom, it transmits the packet to the next hop. It does this over and over, incredibly fast, for every single packet.
Now, you might be wondering, why go through all the trouble of chopping data up just to store and forward it again? Well, in a word, efficiency. Packet switching is literally a masterclass in handling bursty data. Those unpredictable, massive spikes in internet traffic. It allows multiple users to dynamically share the exact same network resources at the same time, using something called statistical multiplexing. Basically, if your computer takes a breath and stops sending data for a microsecond, someone else's packets instantly swoop in to use that bandwidth. It's exactly what keeps the whole system from collapsing under its own weight.
And look, this isn't just abstract theory. This is the absolute bedrock of the tech you're using right now to watch this. Grounding this in reality, packet switching is the foundational technique in Ethernet networks. It's what makes your Wi-Fi function seamlessly, even when everyone in the house is connected at once. It is, for sure, the absolute backbone of the global internet itself. Okay, so our data has been perfectly broken down. The packets are completely standardized, they're loaded with their destination addresses, and they are ready to move. But where do they actually go? How do they find their way through the massive, chaotic web of global infrastructure? Well, that brings us to our next major concept. We're zooming out from the data itself and entering the vast environment it travels through.
Part 2. The mechanics of routing.
Think of it this way. If packet switching is what preps the data, routing is the strategic mastermind mapping the journey. It's the whole process of determining the absolute best path across a chaotic network. Routers aren't just taking a quick glance at a destination address. They're actively evaluating the entire environment. They're analyzing network topology, checking real-time congestion levels, and dodging dead links on the fly. Now, what's really fascinating about this is exactly where all this decision-making happens. If you look at the OSI model, routing operates strictly at the network layer, layer 3. This is where routing algorithms and complex routing tables are making rapid-fire optimization decisions based purely on IP addresses. The whole goal? Minimize delay and absolutely guarantee reliable delivery. So, how is this managed? There are two primary ways: dynamic and static routing. Dynamic routing is highly adaptable. Routers are actually talking to each other constantly to update their pathways based on real-time network conditions. Like, if a massive fiber optic cable gets cut somewhere, dynamic routing instantly calculates a detour. Static routing, on the other hand, is much more rigid. With static, the exact pathways are manually locked in by human network administrators. It doesn't adapt, sure, but it offers absolute, predictable control over exactly where the data flows.
To put this into a real-world perspective, let's look at protocols like BGP and OSPF.
BGP, or Border Gateway Protocol, is essentially the postal service of the internet. It's like the digital duct tape holding massive, distinct global networks together. Meanwhile, OSPF, Open Shortest Path First, is this hyper-efficient algorithm hunting for the absolute quickest internal route within massive enterprise networks.
Part 3. The Modern Network Synergy.
Listen, if you take away anything from this explainer, let it be this fundamental distinction. We are looking at a method versus a process. Packet switching is the physical method. It's the technique of transmitting data by breaking it into manageable pieces. Routing is the logical process. It's the decision-making system determining the ultimate path for those pieces to reach their home.
So, the crucial point is this subtle but immense difference in scope. Packet switching is a mechanical technique utilized within a network to efficiently manage bandwidth and share resources. Routing, however, is a strategic process that guides that data across a vast web of interconnected networks.
Let's see how this builds together. Ultimately, these are not competing ideas at all. They're perfectly complementary tools. Think about it. Without packet switching, routing would be totally overwhelmed trying to shove massive unbroken files to a single pipe. And without routing, our perfectly organized packets would just wander the web endlessly, completely lost. They rely on perfect conjunction.
As our source material beautifully summarizes, both concepts are fundamental to modern networking and are used in conjunction to efficiently and reliably transmit data across networks, including the internet. It's exactly this harmony of method and process that allows us all to stream, browse, and connect globally without ever giving it a second thought.
The digital infrastructure all around us is practically a modern miracle of engineering. So next time you click a link or load a website, I want you to take just a brief second and ask yourself, what complex, invisible routes are your millions of perfectly broken down packets discovering and navigating right at this very moment? Thank you so much for joining me on this explainer. Keep learning, and I'll catch you next time.